So as introduced, I'm Jae-Mo Lihm. I'm a postdoc in UC Leuven in the group of Samuel Ponce, and today I will talk about how phonons affect the dispersion and self-energy of electrons, and also how electrons affect the self-energy and dispersion of phonons. And I'll explain two methods: Wannier function perturbation theory, and the so-called two-temperature method for calculating the phonon self-energy, and discuss how they enable an efficient and accurate calculation of this phenomena using Wannier interpolation and the PW software. So let me begin with the first part, the phonon-induced renormalization of the electrons. So this week you may have heard several times about the self-energy and the renormalization effect. But let me begin with a very simplified picture of that phenomena. So suppose you have a variable x which describes the atomic displacements or the phonon amplitude. And at zero, so the equilibrium coordinate, the electron eigenvalue will be a fixed value. But if the electron eigenvalue have a dependence on the phonon displacement, then as the temperature increases, or if you have a 0-point vibration of the phonons, then the phonon distribution will spread out like this blue or red curves, and the average value of this electron eigenvalue or the electron energy would be the weighted average of this electron eigenvalue with the phonon distribution as the weight. So this is a very schematic way of understanding how phonons or the phonon fluctuation renormalize the electron eigenvalue. To make this very simplified picture into something that we can actually compute, we can use Feynman diagrams or quantum mechanical perturbation theory. So you would have seen these diagrams from the lecture of Electron Giustino. And these can be simply understood from textbook quantum mechanical perturbation theory. The first term, the so-called van Mejdal self-energy, comes from a second-order perturbation theory type correction due to linear electron-phonon coupling. And by linear, I mean that we take the linear term in the Taylor expansion of the the electron potential V with respect to the atomic coordinates U. And there is an additional contribution which comes from the next order term in the Taylor expansion, the quadratic term, or the second order derivative of the potential. And now, since we are already at the second order, we can just use a first order perturbation theory, just the expectation value of this operator with the equilibrium eigenvectors, and that gives us the Debye-Waller self-energy. Adding up these two terms, we get the full second order correction to the electron self-energy within the so-called Allen-Heine-Cardona theory. One of the most common manifestation of the Allen-Heine-Cardona theory is the thermal reduction of the band gap. So as you increase temperature, phonons tend to reduce your band gap of a semiconductor, of an insulator, or an insulator. To understand that, let us consider this simplistic band structure and consider the van Mejdal self-energy. The correction or the van Mejdal self-energy at the conduction band minimum states will be dominated by contributions from nearby conduction band states, because those are the states that are close by in energy, so they will have the smallest denominator, and the overall contribution should be the greatest. And the sign of that contribution is negative because the denominator is negative. And this is basically a band repulsion. So you have a conduction band minimum state and another conduction band state, and they repel each other, so the conduction band minimum state is pushed downwards. Similarly, the valence band maximum is pushed upwards, so the band gap is reduced. This temperature dependence or thermal reduction of the band gap has been calculated in many materials, and qualitative and even quantitative agreement have been found with experiments. For example, in these calculations by Gabriel Antonius and collaborators, they have found a very nice agreement with experiments by combining the density functional perturbation theory and the GW calculation. However, calculating the electron self-energy is a very challenging numerical task, and so far works have focused on calculating this quantity at a handful of K points, like just the valence band maximum and conduction band minimum, but not for the full dense K point mesh throughout the full Brillouin zone. The reason is that the expression for the van Mejdal self-energy includes two types of summations that are hard to combine with each other. So this equation is the full expression for the van Mejdal self-energy that we actually need to compute. In the numerator, we have the matrix element squared, In the denominator, we have the initial state energy, epsilon nk, and the intermediate states, which is the intermediate state electron plus or minus the single phonon, depending on whether you describe a phonon absorption or emission. And then you have a temperature-dependent occupation factor. But here you have to sum over all types of intermediate states, meaning that you have to sum over both the momentum of the intermediate state phonon and the band index of the intermediate state electron. The solution to the first problem, the summation over the phonon wave vector, is simple. We can use Wannier interpolation. So you can use standard codes like GPW to go from a coarse grid to a dense grid with small computational cost, and you can perform calculations over several hundreds times hundreds times hundreds grid of 2 points. However, the problematic part is the summation of number of bands. Since we are calculating the eigenvalues or the real part of the self-energy, all the intermediate states gives a non-negligible contribution, even if they are very high in energy. So typically, people have found that more than hundreds of bands per atom is needed to converge this quantity. For example, in this plot, you show that for boron arsenide to converge the band gap within reasonable accuracy, one needs to include more than 600 bands per atom. And if you include less bands, then you get these very large fluctuations, so you cannot get a reasonable number. And since Wannier functions are limited to low energy atomic orbital-like bands, it is very difficult to interpolate more than hundreds of bands using Wannier functions. And even if you manage to do this interpolation, for calculating the fine-grained matrix elements or energy would be extremely demanding. Therefore, we need to find a way to get rid of this summation and transform this equation in a form that is more applicable to Wannier interpolation. And so in the following slides, let me explain how, step by step, how we can transform this seemingly complicated formula in a way that can be easily Wannier interpolated. And I will explain in 3 steps. The first step is to separate the active space and rest space contribution. So the active space means the states low in energy, close to the Fermi level or close to the valence band gap that you Wannier interpolate and that you are interested in. Typically, you're not interested in the very low energy semi-core bands or very high energy plane wave-like bands. So we call them rest states. If you want to calculate the self-energy for some state in this active space, like the valence band maximum or conduction band minimum, then the contribution from the rest space is very far in energy. They are separated in energy. So the difference between the active space energy and the rest space energy is much larger than the phonon energy. This means that in this expression for the Van-Migdal self-energy, one can approximate this expression by neglecting the phonon energy in the denominator, because the difference between the rest space, active space, and rest space is already very large. One can drop also this in small infinitesimal imaginary part, and also the occupation number factor cancels each other when you add phonon emission and absorption. After this approximation, you find a simplified form of the rest space Van-Migdal self-energy, which no longer involves the phonon frequency. It just involves the matrix elements and the electron energies. And now, but still you have the sum over infinite number of bands. So now we want to get rid of this sum by transforming this expression in terms of the wave function perturbation. The idea is very simple. So if you recall from quantum mechanics, but you can remember that not only the second order perturbation of eigenvalues, but also the first order perturbation of the wave function involves an infinite sum over bands, or infinite sum over states. The perturbation of the wave function psi mk with respect to the atomic displacement u involves an infinite sum over the intermediate state wave functions n. And this expression exactly identical to this expression called this colored terms that appears in the rest space Van-Migdal self-energy. So you can just remove these complicated matrix elements and the summation and replace them by this wave function perturbation. Now this is just rewriting the same quantity, but now the sum over bands is made implicit in this wave function perturbation. So you may wonder, this is just rewriting the same quantity and hiding the some more bands in this wave function perturbation. So you may wonder, what do we gain from this? First, what we gain from this is that we can easily calculate this wave function perturbation without doing an explicit sum over bands, and instead by solving this linear equation, which is called the Sondheimer equation. And this is implemented in many plane wave codes like quantum espresso and used to calculate the phonons. And this is how plane wave codes like quantum espresso or Abinit calculate the van Migdal self-energy. Since solving this equation is much faster than doing this infinite sum over bands. However, this is still not enough for Wannier interpolation because still this quantity should be represented in plane wave. So what we finally need is the way to transform this momentum space or k-space object to a real space object in a way that is localized. So that is a reason why we have developed this Wannier function perturbation theory. The wave function, so this expression involves two wave functions, two objects, the wave function and the wave function perturbation. The wave function transforms to Wannier functions by using this gauge transform explained by Junfeng Chao in the previous talk. And if you choose a smooth gauge, then the Wannier functions are localized in real space. Now the question is whether we can derive a similar or an analogous object for the wave function perturbation. The answer is yes, and this is the object we termed Wannier function perturbation. The idea is very simple. Since we are trying to calculate the perturbation of the wave function with respect to atomic displacements, let us calculate the perturbation of the Wannier functions with respect to atomic displacements. So suppose we have a s orbital-like Wannier functions shown here. If we move this atom to the right by amount u, then the Wannier function will also follow the atom to the right. Wannier function perturbation is basically the difference between the two, or the first order coefficient in the Taylor expansion. So if you take the difference between the two, you get this object, the Wannier function perturbation, which is positive on the right and negative on the left. Formally, you can define this as a perturbation, as a finite difference derivative. And if you're interested in the technical aspects, we are using the unperturbed Wannier functions as the initial guess for the perturbed system to ensure maximal smoothness of the gauge. And this construction is useful because since both the Wannier functions of the unperturbed and the perturbed systems are localized in real space, their difference should also be localized. So this Wannier function perturbation is by construction also a localized object. And what we have found in this paper is that one can rewrite this analytic finite difference expression in a form that is similar to density functional perturbation theory. So we have this Wannier function perturbation on the left-hand side, and it can be calculated by linearly combining the wave function perturbation calculated on a coarse K grid using the same gauge matrix U used for calculating the Wannier functions. The only difference is that you have this projection, which projects the contribution within the Wannier or within the active space out, because we're calculating the rest space contribution. So we have to avoid double counting, we need to remove the active space contribution. Now, since both the Wannier functions and Wannier function perturbations are localized, the corresponding matrix element, which we call S here, is also a localized object. So it decays rapidly as a function of R, and therefore we can accurately Fourier interpolate this quantity. So our final expression for the rest space van Migdal self-energy looks as follows. This is just a simple Fourier Wannier interpolation expression for this S matrix element, which is the real space localized object, and we will multiply a suitable gauge matrix to recover the momentum space self-energy in the band basis. As this plot shows that this matrix element indeed decays rapidly by several orders of magnitude in real space, ensuring that this Fourier interpolation is accurate. And by adding the active space van Migdal self-energy, which can be calculated using ordinary Wannier interpolation, and also the Debye-Waller self-energy, which also can be easily Wannier interpolated, we get the full electron self-energy using only Wannier interpolation. So here we have benchmarked our method by comparing the renormalized band structure with the plane wave calculation. The red curves shows the renormalized band structure computed using Wannier function perturbation theory, and you can here recognize the thermal reduction of the band gap as the conduction band moves downwards and valence band moves upwards. The red curves agree very well with the black dots, which are the calculations results from the plane wave calculation, ensuring the correctness of our theory and implementation. In terms of computational cost, there is a huge gain. Thanks to the fact that we can use Wannier interpolation, we can very efficiently calculate the self-energy at a dense mesh or a large number of K points. So for 379 K points, using a brute force calculation using in the plane wave basis, so solving the Steinheimer equation and calculating every matrix elements in the plane wave basis takes more than a million of CPU hours to fully calculate the self-energy. However, using Wannier function perturbation theory, you need to pay a small cost due to the fact that you need to Wannierize everything. But after that, calculating the self-energy, the electron-phonon coupling is extremely cheap, and you can calculate everything with using 100 cores within a day or two. And this Wannier function perturbation theory provides you the renormalized self-energy or the temperature-dependent band structure, and it can be combined with any quantity, any property that you have been calculating this week to see how this band structure renormalization affect the quantity. For example, you may study transport, conductivity, etc., including this band structure renormalization effect. But the property that is most significantly affected, one of the properties that is most significantly affected is the optical properties. So this optical absorption, this indirect optical absorption process, which you have learned from the lecture by Manosio Pakis, you can, since silicon is an indirect bandgap material, you need to absorb a phonon or emit a phonon to compensate the momentum difference. The phonon absorption is allowed only at high temperatures, but its onset is at low photon frequency because phonons give the additional energy, while the phonon emission is available at all temperatures but requires a high photon energy. So as temperature increases from 0 Kelvin to high temperature, the onset of the absorption spectra becomes lower in energy, and the kink here at the onset of phonon emission becomes smoother as the phonon absorption process becomes stronger. So this is one source of temperature dependence, and another source is the thermal reduction of the band gap, which leads to an overall redshift of the spectra. So this second effect, the redshift, can be described only if you include the temperature-dependent renormalization of the band structure. So here we compare the calculation of the optical absorption spectra without the band structure normalization and with the band structure normalization. This second calculation is made possible thanks to Wannier function perturbation theory because it requires a calculation of the self-energy on a very dense mesh of K points. You can see very clearly that without this effect, you do not reproduce the redshift of the spectra, which is seen in experiment, while in the second plot, you nicely reproduce the temperature dependence of the onset and the slope of the spectra without making an arbitrary shift of each spectra to match the experimental onset. So far I've been talking about the self-energy or band structure normalization, which gives a single number that corrects your eigenvalue. And you can generalize it to the calculation of full self-energy by adding a frequency dependence in your calculation. The only term that becomes frequency dependent is the active space Van Migdal term, because the red space Van Migdal term is frequency dependent, but only at the scale of this red space. So it is frequency dependent only at a few electron volts above or below your Fermi level. But most of the experiments are done near the Fermi level at the 1 electron volt scale, for example. So where the frequency dependence of the red space contribution can be approximated to be 0 or can be neglected. And the Debye-Waller self-energy is by definition frequency independent. So what one can do using EPW is to include frequency dependence in the calculation of the active space Van Migdal term and add the static or frequency independent rest space and Debye-Waller contributions to get the full frequency dependence of energy and the spectral functions. So these experiment and theory shows the RPS spectra of anatase TiO2. And here you can see the spectral functions calculated from theory nicely reproduces the multiple satellites seen in experiments. And to obtain these results, one needs to go a step further than simple Allen-Hynek-Cardona or van Migdal theory by adding the so-called cumulative expansion, which gives multiple satellites in the spectral functions. So if you're interested in this kind of calculations, you may refer to these references for further details. So now in the remaining few minutes, let me switch gears and discuss the flip side of the effect, the phonon self-energy induced by the electrons. So just like the electron self-energy, the phonon self-energy describes the probability of finding a phonon at a given wave vector and a given energy. It is often written in terms of the frequency-dependent dynamical matrix, which generalizes the static force constant matrix of the simple static ball and spring model of phonons. And also, one can calculate the spectral functions using the self-energy. Various spectroscopic measurements can give access to these phonon spectral functions or phonon quasi-particle energy. For example, the Raman spectroscopy, inelastic X-ray scattering, or other probes like neutron, electron energy loss, or infrared experiments can all give direct or indirect information about the phonon self-energy. This shows that the experimental measurements agree very nicely with calculations using density functional perturbation theory plus the electron-phonon self-energy. And here, from these experiments, you may notice that the experiments are done on doped graphene or doped diamonds. So the electron-phonon contribution is significant usually in doped materials or metals because you need free carriers that the phonons can interact with. But there are also other sources of phonon self-energy, which are the phonon-phonon interaction in anharmonic materials or disorder effects in polymorphous structure or due to isotope mass disorder. So using codes like this, for example, you have tried the DG code yesterday, you can reproduce the phonon self-energy and spectral function due to phonon-phonon interaction and disorder effects. But today in this talk and the tutorial this afternoon, we'll focus on the electron-phonon contribution, and we will use MgB2, which is a metal, as an example. So I will not go into the technical details of the theory of phonon self-energy. Those who are interested may refer to the lecture slides of Feliciano Giustino on his many-body theory talk. But let me briefly mention that the phonon self-energy can be calculated as a product of electron-phonon coupling, the bare electron-phonon coupling, the electronic substitutability, which depends on the temperature and also on the doping, and the electron-phonon coupling, which is the screened electron-phonon coupling. And here it is important to note that this screened electron-phonon coupling is in principle dependent on the frequency that you're calculating. However, this self-energy transformed this bare phonon Green's function to a renormalized Green's function. But in actual practical calculation, we do not have access or we do not care about this fully bare phonon Green's function. Our starting point is actually a density functional perturbation theory calculation, which already includes some sort of renormalization or phonon self-energy effects at the level of that density functional perturbation theory. So we have to be careful to avoid double counting the self-energy twice. But in DFPT, you make certain approximations, like the approximation of high temperature due to a limited K-point sampling. And also you do a static calculation, or you use the Born-Oppenheimer approximation, so you calculate everything at zero frequency. Using EPW, we would like to calculate something that mimics experiment. So we want to calculate the self-energy at low temperature and at finite frequency, typically that of the phonons. So what we have to do is to take the difference between these two, the difference of the self-energy, the low temperature, finite frequency self-energy, and subtract the high temperature, zero frequency self-energy to correct the density functional perturbation theory phonons. So this expression shown in purple gives the correction term to the self-energy. And this now involves two screen vertices calculated from the FPT. This is an approximation that is accurate up to first order in the difference between these two. If you want to go to higher order, then you need a frequency-dependent vertex which is usually not available in first principle software. So in the tutorial, we will use this expression, calculate the low temperature and high temperature self-energy using EPW, subtract the two, and add this correction to the phonon frequencies, the DFPT phonon frequencies, to finally get the renormalized phonon self-energy and spectral functions. So to conclude, I have discussed the phonon-use electron self-energy and the electron-use phonon self-energy, and how the development of new methods and implementations enable us an accurate and efficient calculation of these phenomena. Those who are interested can refer to these references for further information. Thank you for your attention.
Is there any question from the audience? Yeah. So, how do you define the rest bands in your space? Like, are they in the HCF calculations, or they're one-yearized, but they're not included in the EPW space?
So you're asking about the red space, right? Yeah, so in principle, it is also a convergence parameter. So you need to expand the active space as much as possible as to converge your self-energy. But this means that you need to do the computational cost increases. So usually what one can do is to identify an energy range of you want to calculate, and then add a few electron volts of buffer on above and below to make sure that this approximation is valid. So the phonon frequency is much smaller than this buffer region. And then you can Wannierize this active space, choose a Wannierization that includes all these active space bands, and then define the remaining bands as the red space bands.
Okay. What are the ingredients for this technique? Like, you need to do DFPT first. Where do you get the PD, the response to the potential to perturbation?
Yeah, so thanks for the question. So you have to, so the ingredients are almost the same as usual EPW calculation. You have to do the FPT. You need the Wannier functions. The only additional ingredient is that you need this wave function perturbation. So in the tutorial, we will have additional step in the workflow that calculates this wave function perturbation and this matrix elements in the coarse grid of coarse K-point mesh. And then using EPW, we will transform them to real space and then perform Wannier interpolation. So this is the only additional ingredient to the usual EPW workflow.
That's okay. Hi, I'm wondering how much displacement do you use to get the perturbation of Wannier function, and also are they orthogonal to each other?
Yeah, thanks for this important question. So we are not actually using any finite displacement to calculate these Wannier functions. So this is how we formally define these objects. But doing a finite difference calculation using supercell is very costly. What we do instead is to do DFPT. So we calculate only the linear response of the Wannier function. So it does not involve any finite steps or differences. It just involves this derivative calculated directly from DFPT, and also this is just the direct derivatives. And yeah, they are not orthogonal to each other, but they are orthogonal to the Wannier